Okay, so this is the second video in my series on nutrient requirements, and in this one I'm still really covering the basics, and so we're going to look at some of the issues relating to studies and trials. I'm going to express some of my opinions and give you some understanding of things that I believe we need to realize before we just accept that a published nutrient requirement is the best one for us. So why do we need to know about nutrient requirements? Well, what's most important is we need to know the requirements for what we classify as essential nutrients. These are also known as indispensable. These are nutrients that must be provided in the food for the animal to grow and develop at its maximum genetic potential. They are unable to be synthesized de novo, that means inside the animal, at a rate that meets the animal's demand. So they're not being made there at all, and have to be coming in with the dietary source or coming from the water or elsewhere. And among these, we generally consider essential amino acids, essential fatty acids, vitamins, especially vitamin C is the most famous one of these. And then we have minerals, macro and trace minerals. And then we have cholesterol in shrimp. Now, normally we don't consider cholesterol to be essential in vertebrates or fish, but it is essential in shrimp. And while I'm on this page, I'll just mention that you see there at essential amino acids, I have this mnemonic. And so this was told to me by my professor, Dr. John Halver at the University of Washington. He was a retired lieutenant colonel in the U.S. Army Reserve, and he had this mnemonic, which stands for Private Tim Hall. So private, of course, is the lowest level of a soldier in the Army. And so let's go through it. So P is phenylalanine, V is valine, T is tryptophan, T is threonine, I is isoleucine, M is methionine, H is histidine, A is arginine, L is leucine, and L is lysine. There you go. Now, we also have non-essential nutrients, and these are also known as dispensable nutrients. These are nutrients that the animal can synthesize from other compounds at a rate that usually does not limit the animal's growth or development. Therefore, they are not essential in the diet. And in some cases, we have some non-essential amino acids that are sometimes made from essential amino acids. And this is why we sometimes hear about somebody might say cysteine spares methionine. And you see here on my list of non-essential amino acids, I have cysteine being made from methionine, and we have carnitine being made from lysine and methionine. So if we supplement carnitine in the diet, then we spare lysine and methionine for other uses. And so this is one of the reasons why sometimes we want to supplement these amino acids in the diet, is in order to allow them to be used for the right things rather than the things that are converting them into non-essential. And then we have phospholipids. So phospholipids are generally in vertebrates and in fish are considered to be non-essential nutrients. But in the case of crustaceans, phospholipid synthesis, like in shrimp, for example, phospholipid synthesis is very slow. And when we're having these animals grow at a rapid rate, it's generally not enough. Now, we have conditionally essential nutrients. And while we would classify these as dispensable, I have this quote that I've taken from this paper by Mishley and et al. From 2014. And Mishley is talking about conditionally essential nutrients in human nutrition. So I have just put it here, but I've made some slight changes down below in the material that's inside the quotation, inside the So we have conditionally essential nutrients, and while we might classify these as dispensable, they are nutrients which, as this quotation from Mishley says, conditionally essential nutrients are those that can usually be synthesized in adequate amounts endogenously but may require exogenous supplementation during some circumstances. In some cases, these increased requirements can be a result of impaired absorption, increased anabolic requirements, and increased metabolic demand. And inside the brackets, I've given you some examples of things that would cause these nutrients to be conditionally essential. Now, it's important to understand that nutrient requirements are dynamic. All of these factors in this table can affect the metabolism, the physiology, the general operations of all of the cellular functions going on inside the body, and then absolutely they will affect nutrient requirements. And feeds may meet nutrient requirements and are balanced according to what we understand, but sometimes feed and farm performance is reduced but cannot easily be explained. Now, when we talk about water temperature goes down, feed intake goes down, growth goes down, okay, some of those are easy to understand. But when we start talking about things like the effect of pathogens, parasites, infections, disease, impacts on immunity, and then also interactions with other nutrients, then it becomes harder to explain why we might have some issues with our set nutrient requirement levels. Now, when we're talking about limiting nutrients, essential nutrients, we usually use this example with amino acids. It's called the Liebig's barrel. And so what we see in the first one here is lysine is quite severely limiting right here. And so the water in the barrel, and you can see the water there, the water in the barrel can only rise to the level of the lysine. And so all of this above here is all potential, but it's unable to be used because the limiting amino acid is lysine. Now, if we add synthetic lysine and we raise the lysine level, for example, up to this level, then methionine becomes the limiting amino acid, and the water will fill up to that. Now, we've increased the potential, but we still have some that are not going to be used. Now, these don't sit around. If they're there for any long period of time, the animal will use them in some other way. And when we're talking about aquatic animals, the most obvious thing that happens is that they're broken down and used to provide energy, because these things just do not sit around. And so I use this example of building a wall and what happens when we don't have the right brick. So we start down here at this area, and we have a problem with this guy right here. We have a deficit of this one. And so if we go beyond that, we're building our wall, and we get up here and we don't have it, then growth simply stops. The protein synthesis simply stops at this point. And let's say we find one. We don't have a total deficiency, but we have a partial deficiency. We then find this one, and on we go, and we're building this thing here, and then we come to the next one and we don't have this one, and then once again we stop. Now, if we don't have a deficiency, then of course we go to the end of the protein, and we then start looking to make another one after this one is completed. So that's the idea, and it works with vitamins, and it works with other things like essential fatty acids, which are necessary in the construction of cell bilayer membranes. Now, I just wanted to highlight this paper, which is a very old paper from 1964 looking at iodine. And this was done with iodine requirements of Chinook salmon. So you see over here that they have a basal diet. So this is basically Dr. Halver's H440 laboratory diet. And we see that there's a mineral supplement here. And so what they've done is they've made this diet and they have a premix with the minerals all in, and they have a premix with minerals without any minerals in the ration at all. And then they have some that they've made that have differing levels, as we can see here. So what we look at with this is when we feed the fish the diet that has no iodine, growth does not occur. Why? Because iodine is essential for the thyroid gland to be able to make growth hormones, the T3, T4 growth hormones. Now, if we suddenly put the full amount in the diet, then growth starts again, as you can see here. But what they've done here then is they've then also added some, but not the full amount. And they can see at some very low levels, basically growth does not occur down here. And so as they add in some here, well, we can see this some growth. And then over here in the text on the side, what they've noted was that for Chinook salmon fingerlings, that the requirement was not more than 0.6 micrograms per gram of dry diet. Whereas for advanced par, now advanced par are animals that are almost ready to smolt. These are salmon, so they go from freshwater and then they migrate into the sea, and that process is called smolting. And so when the animals are preparing to enter seawater, the requirement is approximately doubled to 1.1 micrograms per gram of diet. And they assume that that's needed for the process of smoltification, although it may go down again later, as we've seen with some other nutrients. Now, I admit that for a number of years I had been a consultant for DSM, consulting with them for technical issues related to vitamins and enzymes and so on. And so this is a graphic that they have prepared in relation to what they call optimum vitamin nutrition. And I wrote a booklet, a white paper for them on optimum vitamin nutrition for warm water aquaculture. So what we want is we want our vitamins to be in this range right here. When our vitamins are in this range, then we have optimum amounts that can compensate for negative factors that reduce animal performance. So we see optimum metabolism, optimum growth, optimum immunity, and optimum well-being, which is related to basically health and fitness. Now, we might sometimes see a situation where if we don't have quite enough, if we use the levels that we get out of the books without considering that our production system might be destroying some, or we might have poor storage conditions that leading to even greater losses, we often might find that animals are in suboptimum range, in which animals will grow but performance may suffer due to subclinical deficiencies and limitations on metabolism, their ability to deal with stress and immunity, and so on. This, I believe, is much more common that we understand because it's very hard to diagnose. And then we have what we classify as nutritionally deficient. So this is maybe when somebody in the factory forgot to add the vitamin mix totally into the batch of feed. That would be an example where we might be totally deficient. And we might also have people not considering production losses during our processing in the feed factory. And so if we end up being really nutritionally deficient, then the first thing that happens in almost every case for almost every nutrient is that feed intake goes down. We start to see some deficiency signs, growth slows down, we see poor health, and in the end, we see poor survival, a lot of mortalities on the farm, and the farmer is going to lose money for sure. Now, when we talk about minerals and fat soluble vitamins, their dose response curve looks something like this. Now, this is from Santosh Lal, and he's talking about minerals. So we see that we have a deficiency, but when we get enough, we can meet the dietary requirement. We have an optimal level, which is fairly flat because this individuals are different. And at some point or another, we reach a maximum tolerable level. And then if we add more, we can actually reach some kind of a level of toxicity. And if that carries on even to greater concentrations in the body, or it carries on too long and becomes like a totally chronic situation, we can end up with death. So this is very similar to with vitamins to hypervitaminosis. And this is applicable to the fat-soluble vitamins. Vitamin A and vitamin D are known to be causing hypervitaminosis. That is, if you overdose on them, it can be have a negative effect on many systems inside the body. Vitamin E, because it's mostly used in cell membranes to help to protect the membranes from oxidation, it's quite rare to actually have hypervitaminosis. And vitamin K, it has a number of functions. The best well known is as a factor affecting coagulation in the blood, and it's basically, we could say, no. An overdose of that would be extremely unlikely to cause a hypervitaminosis situation. So when I was looking at that table, and I mentioned that nutrient requirements change with the environment, this is from a paper talking about the effect of hypoxia, or in other words, oxygen depletion on food consumption and growth. And so on this axis we see here, we have temperature on this axis, and we have oxygen on this axis, and we have growth. And you can see that there's an area up here which is the optimum temperature, which is about 20, I suppose. And 100% saturation, we get maximum growth. Now, if we have less oxygen, even if we're at optimum temperature, growth rate goes down. If we are at a extreme temperature, this might be actually cause mortality. Or if our temperature goes down very low down here, then of course growth stops again. So this is an indication of how nutrient requirements can change the effect. And in this case, we're looking at bioenergetic model predicting feeding and so on. Now, once again, referring back to that table, nutrient requirements change with fish size. So we see here weight gain. So this is the weight of the animals as they grow. And we see here the dietary lysine requirement as a percent. And so as the animals grow, the dietary lysine intake will grow. And this is a paper from Norway. So when we talk about research for nutrient requirements are usually estimated by feeding research diets. So these are diets like Dr. Halver's H440. They're very purified ingredients, usually bought from laboratory supply companies. So we feed these diets with graded levels of the individual nutrients that we're interested in, and we feed them to a uniform group of usually small, healthy animals grown under optimal conditions in a lab. And really, my main comment here is this does not represent real world conditions. And so this is the first thing we need to wonder about when we see these published requirements. Are they really applicable to my animals in my farm? Because when we talk about it's not real world, it's a stable, controlled environment. The water quality is high, oxygen levels are high, and feed is highly digestible, and the quality of the feed is very consistent. Now, all research trials suffer from a few things. So we have space, budget, and time limitations. So most nutrient requirement research is conducted with small animals in aquariums in a laboratory, maybe small tanks, but we have a limited number of those. The number of replications per treatment are often the minimum required because we have a limited amount of tanks available to us. And then the other thing is because money is time, we often find that these experiments are run on a few weeks, a month, 2 months, 3 months, generally never more than that. And of course, the issue is that when we feed fish in a trial, as they grow, they need more feed, right? And so we're going to measure some way, whether it's at the very basic level. We might measure feed intake, we might measure growth, we might measure survival. In the past, we would often measure liver saturation, and we might measure body and tissue retention by analyzing those tissues and seeing what was there at the beginning and what was there at the end. More recently, with molecular biology, we have enzyme activity markers and we have gene expression. And at the right, I have this graphic which just shows you the old way we used to measure growth response, which was just simply feeding, and we see a different growth, and then we put those lines on there and we determined the break point. Now, that's how it was done before, but it's not really very applicable today, and I'll show you why in a moment. So in the graphic, we see here the first are those observed points, and so we can analyze them in many different ways, and each researcher and laboratory oftentimes has their preferred methods. So we have linear inflection point, we have the broken line model, which is this one over here, and then we have polynomial models, this one, and then we have different, like this one is measuring saturation kinetics, what's the maximum that we can achieve. We have this one, which is also like a maximum value. And then we have statistics, and so we've got a bunch of those, analysis of variance, analysis of covariance, and then multiple range tests, of which this is an example up here. We often see tables with A, B, C, D, E telling us which ones are statistically similar and which ones are not. But Professor Halver always used to say that if the experiment is really a success and the results are really obvious, you should never need statistics to declare a solution or to declare a result. They should be obvious. So this is an example of a polynomial equation on this curve. And so if we look at this, we would say, well, this is the maximum point right up here, isn't it? But what these people are doing, they say that the dietary requirement is considered to be that nutrient concentration which promotes 95% of the maximum growth response. So for these people, and this is from Malcolm Jobling, he's a Norwegian, and he's very knowledgeable on this particular kind of a topic. He would say that you should be a little bit conservative and set it at 95%. Now, it's very important when we're doing nutrient requirement studies that we have proper experimental design. And this is one paper that I highly recommend that you find. And the QR code is here. This will allow you to find this paper, and I believe you can download it from that link. Often when I'm searching for these kinds of papers, I search in Google Scholar, and if the paper is available as a free download as a PDF or something from somewhere, I will copy that link and I will paste it here for you to be able to download them. So this is Carl's paper. So he says, common mistakes, not enough treatment levels to extend analytical range. So what do we see here? Well, we see that this curve, this line is increasing, but it hasn't leveled out. It hasn't started to decline. And so we must need to continue on beyond this point until we reach an inflection point, and this experiment does not. We have not found the maximum nutrient level. And so this, then, if they were to say, but this is the requirement, no, that's totally wrong. We might see that treatment levels are too far apart to catch small but significant events. And so we see here, this is also common in the past, where we have these lots of levels at the smaller size. And then we said, well, let's just check and see if it might be a lot more than that. And so we set this one. But then we do a broken line analysis and we say, well, this is the amount we need. But if we do it on a polynomial basis, the polynomial will be, well, there's an inflection point up here somewhere, and we've missed it because we don't have any points here in the middle. We need to have more, and we haven't done it. So this would also be considered to be a very poorly arranged experiment. And there's nothing that we could do except do it again and fill in these gaps. Now, this is an example where we have not enough data points, and this is what we see over here, similar to what we just saw, where we have 5 over on this side, and then we have 1 way over here, and we don't know what's going on in the middle. Now, what we have in the second graph is that they've actually filled in that with some points, and we can see that this was the highest one. There's a gentle decline going on right there. And so then if we were to say that this is the requirement right here, we actually have data points to show that that was the highest level. So this is an example of a successful way to do this, where on the left it's not. Now, sometimes we're not going to be using the right type of model for estimation. Now, before we understood a lot about how to use polynomial models, and that had not really come into effect yet. Most everybody was doing these broken line models, and we estimated the requirement at the breakpoint. Now, notice that when we use a polynomial instead, that we're getting a result higher than 6. But when we use a broken line model, the requirement is over 4, but under 5. And so what we would do is we should take our data set and we should use different methods of analysis. We could do broken line, but we should do polynomial. We should do the different methods, and to find the one that seems to make the most sense. And if you look at this and you look at this, you say, well, if we're using this one, maybe we're going to actually underestimate the requirement. But this one is more likely to be more correct. Now, one of the things is that when we're dealing with fish, and generally shrimp too, is that the weight gain needs to be several multiples of the starting weight. Now, if we're dealing with larvae, fish that are weighing 0.1 grams, to get them to 1 gram, I mean, that's a very big jump. But if we're starting with a fish that's 200 grams and we need to grow it to 400 or 500 or 600 grams, one, it's slow and it takes a lot of feed. And so we might be tempted to just say, well, I'll just double the weight. But in some cases, especially if we're trying to do requirement studies, just doubling the weight won't show you anything, and you'll make the wrong estimate. And then some of us here in Asia, we've also come to the conclusion that when we have an experiment and we're trying to measure growth as a parameter, now this could be a requirement study or any kind of a study, that the daily weight gain should be at least 80% of the weight gain obtained by commercial operators. Why? Because growth rate affects requirement. And if your growth rate is too slow, your requirement will be an underestimate. And so we would say that when we get slower growth, slower than 80% of commercial, then this is an indication there's a problem with the experiment, with the management of the trial, with the diets, or experimental conditions, of which low oxygen is always the first suspect. When oxygen levels are too low, this suppresses feed intake, it suppresses growth rates. And then when we have growth trials, and as I mentioned before, time is often a factor that's considered by researchers. The trials are too short, and with large fish, that can be quite expensive to have slow growth rates, and we need to grow them for months and months and months. And then in mineral and vitamin trials, the test animals have not had their storage reserves depleted before the growth trial starts. And so Dr. Halver made very certain that he fed animals a vitamin deficient diet for the vitamin he was interested in for some period of time. And some vitamins are depleted very fast, maybe in a matter of a week. But he also found that when he was testing like vitamin B12, folic acid, he actually had to run the fish for almost a couple of months before they got to the level of being depleted. And then deficiency signs would show up, and then he knew that he had reached the point where a trial to determine a requirement would be able to start there. So it's important when we're talking about these kinds of experiments to understand experimental design. So I provided here some resources, and I showed you the paper from Carl Scherer. He's focusing only on fish. He was at the United States Fish and Wildlife Service lab in Seattle, Washington, and then he moved to the university in Norway. We have two papers there at the top. The barcodes are there. And then another researcher that I really, really like, he has some excellent papers, is D.H. Baker. He's a swine researcher from the University of Illinois in America. And you see there are problems and pitfalls in animal experiments designed to establish dietary requirements for essential nutrients. And he talks a lot here about not depleting minerals and not depleting vitamins and so on before you start the trials, and it will give you a poor estimation. And then he talks about the other paper there, animal models in nutrition research. And then the third one, comparative nutrition and metabolism. Okay, now this one is not specifically about experimental design, but for me this is an extremely interesting paper because he asks a bunch of questions like, why is amino acid metabolism like this? Why isn't it like that? Why does this amino acid do this here but doesn't do this there? And so he had, I don't know, 10, 14, 15 questions that he asked, and they're all very interesting questions. So I am recommending that one. You look at that one too. And then we have G.M. Pesty. He's a poultry researcher from the University of Georgia. And you see here a comparison of methods to estimate nutritional requirements from experimental data. So this would be the guy who's going to be able to tell you which is the right statistical model, which is the right visualization, whatever you need to do with your data in order to be able to determine the correct solution. Now, I cannot do this without mentioning Dr. Brett Glencross. He's a fish researcher in general, but he's also done work with shrimp. He's also done work with lobsters. He was at CSIRO, a government agriculture research organization in Australia. Then he moved to the University of Stirling, and more recently he has moved to be managing research at the International Fish Meal and Fish Oil Organization, or IFFO. And he has lots of papers. I really like his work, particularly papers like this one, where he's talking about factorial approaches. He's got one here. This is for trial catfish. This is for Pangasius in Vietnam, and he has one here for barramundi, or Asian sea bass. These are trials conducted at different protein levels, different energy levels, different temperature levels, different size levels. With barramundi, he's gone from fry up to 3 kilogram individuals, and it has done a wonderful job. And then this one is the summary. The nutritional management of barramundi is the basically the reference, and this was a report for the Australian government, very easy to find online. Numerous other papers, okay, and every single one of these papers that I'm showing you right here, Brett Glencross is the primary author. So rather than giving you a code for everything, I've just simply given you the code for Brett Glencross on Google Scholar. So this is his profile page on Google Scholar. And all these papers will be listed chronologically. You can click on the year link, and they will all line up from beginning to latest. And then many of them you can click on them to look at them, and many of them will have freely available papers that you can download. And lastly, I would like to mention these researchers from India, Zara and Khan. And Dr. Khan, he actually came to my university in Seattle to study with me and Dr. Halver. And then he went home, and he's running a laboratory, and he uses Dr. Halver's study protocols, but not using those 1960s, 1970s techniques. He's using the latest molecular biology and the modern analytical techniques. And I've also given you then his QR code for his profile on Google Scholar. So what's interesting? Well, if we look at these tables, we see, first of all, the first one is requirements with Zara that he did on amino acid requirements. And this is only for Labio rohita, the Indian carp. And you see he's tested many different things, simple ones, fancy ones, RNA, DNA ratios, and so on. And he's determined these requirements. So he's basically still using Dr. Halver's protocols. And then the bottom one is actually the vitamin requirements of snakehead. And once again, multiple methods of analysis, lots of RNA, DNA ratios, and so on to assess growth. And so I recommend that you go and look at his work because he's a modern researcher who's really done a good job in applying Dr. Halver's original methods that were. Dr. Halver, of course, was known as the father of fish nutrition, and the reason for it was because he was the one who developed the research diet, the H440, and he developed all of these original research protocols. So this is a paper, a research group that I highly recommend. Now, Dr. Khan has done work with several other people on other species like stinging catfish and other carps, and you can go and search in Google Scholar and you'll see all of those listed there as well. So my conclusion is that there are often multiple studies on the same species with different recommendations for the same nutrient, but it's highly dependent on the choice of the fish, that is the breeding of the fish, where they come from, whether they're healthy, what size they are when they come into the lab. It's dependent on also the rearing conditions. Some researchers understand research protocols and statistical analysis well, and others not so much. And so that's why I'm recommending going and looking at people like Dr. Baker and Dr. Shearer to learn how to do this well. And really, really good research is hard to find. And it's partly we often find that researchers have their preferred analytical tools, and they often don't update, they often don't revise, they often don't learn how to use better, more complete techniques. And so when we go back and look at an old paper, is that a nutrient requirement determination that we can trust? In some cases, we don't have a choice. But if we look at old papers and new papers, we will find that there are sometimes not significant differences. We're in the range, but the thing with modern is that our ability to test many other things that are all correlated is much, much simpler. So that's the end of this video, and you can find me on YouTube, you can find me on X, and you can find the audio from these videos on Apple Podcasts. And this is a beautiful blue tilapia from Surin, Thailand. Thank you very much.